Okay, this is our last video for our weak acid calculations. In this video, we're going to be focusing on the percent ionization of a weak acid. So if you can jump down to number 5 for me. So here we have hypochlorous acid. We're given the Ka of it, and then it wants us to find the percent ionization. I always use ionization. I only have dissociation there because of the textbook, and it gives us the initial concentration. So here, because even though we're looking for the percent ionization, which is actually going to end up looking very similar to one of the checks we've been doing, we're going to start it in the same process. So let's go ahead and write our balance equation, HClO. Hopefully you're becoming more comfortable with this. And then it's going to be reacting with water, which is going to again act as our Bronsted-Lowry base. That weak acid is going to donate a proton to water to form our hydronium ion concentration. And then we have the ClO, -1 ion left over, which is just the conjugate base of our weak acid. Here I'm going to start my ice table and remove the pure liquid, water in this case. I also kind of jumped ahead. I've been writing my Ka expression early on. So here you have your concentration of your two products times the ClO minus over the weak acid's concentration. All right, so going ahead, we were told that the initial concentration of our weak acid was 0.4 molar. We're going to say that the concentration of hydronium is 0, because again, we're making that assumption that the concentration of hydronium from the autoionization of water is less than 5% of what the hydronium is going to be in solution. And then initially there's no conjugate base of the weak acid in solution. Using our balance equation, we know that we can the weak acid is going to decrease by -1x, and our two products are each going to increase by +1x. And then we're setting up the expressions for at equilibrium. All right, so in this case, because we're looking for percent ionization, really we just need to initially find our concentration of hydronium, just like in examples 3 and 4, and then instead of doing a pH calculation, we're going to do percent ionization here. So for this, we're going to go ahead and use, we were given the Ka, so we're going to have our 2.9 times 10 to the -8. We have x times x, and then we have 0.40 minus x, which again, we're going to say that that change is going to be less than 5%, so we can simplify that. And then going ahead, cross multiplying, taking the square root, you're going to find that x is equal to 1.1, keeping to the 2 sig figs, times 10 to the -4 molar. Okay, which remember that is the concentration of our hydronium. So I'm going to go ahead and fill in the rest of this into the table, which again I think is just a good habit as we move forward. And then when we subtract x out from this, because of how small it is, we're going to get 0.4. All right, so that was our initial step here. Now our percent ionization is going to be essentially the same as when we do our check of our change being less than 5%. Because how we're going to do this, we're going to have HClO, that ionized, okay, which really, that is just X, which is really just the concentration of our hydronium, okay, over the initial concentration. Times 100. So we got the concentration that ionized, which is the concentration of hydronium, or our change of x there, is going to be 1.1 times 10 to the -4 that we got over our 0.4 times 100. So when you get that, you get 0.028, keeping with the 2 sig figs, in this case percent. Which that is also the check to show that that change of x was less than 5%. So we're just going to add in there, and I'm just going to put a little box because that was our answer that they were looking for, that is less than 5% as well. Right, so it's very easy, very similar to the last calculation. The only difference is doing this percent ionization calculation once we find our concentration of hydronium. And that's it.